Using graphs to solve an absolute value inequality. In example 1, we asked to solve for x and we are given that the absolute value of x plus 4 must be less than or equal to 6. So I'm going to take my inequality and separate it into two graphs. The first graph is going to be the graph of y equals to the absolute value of x plus 4. I'm going to call that graph f of x, and that is the absolute value of x plus 4. The second graph that I'm looking at is the graph of y equals to 6. I'm going to call that g of x. Let's draw these graphs. So the red graph is the graph of the absolute of x plus 4, whose salient point is at x equals to negative 4 and y equals to 0. So let's just label it. So we have f of x is the absolute of x plus 4. Then we have the green graph is the straight line y equals to 6, but we labeled it as g of x equals to 6. We notice that these two graphs intersect at x equals to negative 10 and x equals to 2. So to solve this inequality, we must find all the y values of the absolute value graph that is less than or equal to 6. Now, having a look at the arms of the graph, do you notice that if you look at all values of x greater than 2, then the absolute graph lies above your straight line graph. So the absolute value graph's y values will be larger than 6 for all values of x greater than 2, and similarly for all values of x less than negative 10. So our solution are the x values that lie between negative 10 and 2. So we say that x must be smaller than or equal to 2, but greater than or equal to negative 10 for all real values. Because between these two x values, the y values of the absolute value graph are less than those of the straight line graph. That is, they are less than 6. We may also write this as using square brackets because we're including negative 10 and 2 in our solution. We may formalize this by saying that if we have the absolute value of x less than or equal to a, then x is less than or equal to a, but greater than or equal to negative a. In our question, x was less than or equal to 2, but greater than or equal to negative 10. Similarly, if the absolute of x is greater than or equal to a, then x will be greater than or equal to a or less than or equal to negative a. Using graphs to solve absolute value equations, example 2. In example 2, we must solve for x, and we have the inequality x squared greater than or equal to the absolute of x minus 2. So once again, we have two graphs that we're going to draw. The first one is y equals to x squared. That will be the parabola. The second graph that must be drawn is y equals to the absolute value of x minus 2. So let's draw these graphs. So y equals to x squared is your quadratic function, y equals to x squared. Your parabola, and y equals to the absolute of x minus 2 is your absolute value graph with a salient point at x equals to 2 and 0. Now looking at your absolute value graph, we can write down the equations of each of the arms of the graph. For example, this arm here will be y equals to x minus 2 for all values of x greater than or equal to 2, and this arm would be y equals to minus x minus 2 for all values of x less than or equal to 2, and that comes from the definition of the absolute value graph. Now, this is an accurate sketch, so you can easily read off that these two graphs intersect at x equals to negative 2 and x equals to 1. But if you do not draw an accurate sketch, you must find the points of intersection of the two graphs because you need these points to solve the inequality. I'm going to show you how to find these points of intersection algebraically. So we solve simultaneously y equals to x squared and y equals to minus x minus 2. So we say that let x squared equal to minus x minus 2. Simplifying this, we have x squared equals to minus x plus 2. We write this in the standard form because we have a quadratic expression here. So we have x squared plus x minus 2 will equal to 0. This is factorized into x plus 2 times x minus 1. So we see that the two graphs intersect at x equals to negative 2 or at x equals to 1. Now that we found the points of intersection, at these points we need to now find the values of x where the y values of your parabola are more than the y values of your absolute value graph, because your inequality says x squared must be greater than or equal to the absolute of x minus 2. Now, if we look at all values of x smaller than x equals to negative 2, we see that the arms of the parabola lie above the arms of the absolute value graph, or we can say that the y values of the parabola are more than the y values of your absolute value graph. Similarly, if we look at all values of x greater than 1, we have that the y values of your parabola are again larger than the y values of your absolute graph. So the solution to this inequality would be x must be smaller than or equal to negative 2, or x must be greater than or equal to positive 1. In example 3, we need to solve for x. We're given that 4 over the absolute value of x minus 2 must be greater than or equal to 1. Now we had two functions. One is the absolute value of your hyperbola, which is the graph y equals to 4 over x minus 2. And if we scroll down, that has been sketched already. That's the blue graph. So the blue graph is y equals to 4 over the absolute value of x minus 2. Our red graph is the graph y equals to 1. So we must solve the inequality where the absolute value graphs y values are greater than or equal to 1. And again, you look at your points of intersection, you see your graphs intersect at x equals to negative 2 and your graphs intersect at x equals to 6. And it's clearly evident that the answer lies between x equals to negative 2 and x equals to 6. So we will say that x must be less than or equal to 6, but greater than or equal to negative 2. Let's write down the solution. But before we write down the solution, we have something missing from this graph. You can see that with your hyperbola, we have an asymptote at x equals to 2. I'm going to draw it in on this graph. So our asymptote is at x equals to 2 because division by 0 is undefined and we have a restriction, x cannot equal to 2. So we have an asymptote here at x equals to 2. Now, knowing that my x values lie between negative 2 and 6, and I have an asymptote at x equals to 2, I can say that my solution would be x must be, so I can write x must be greater than or equal to negative 2, but smaller than 2. Because we have an asymptote, x cannot equal to 2. Or x must be less than or equal to 6, but greater than 2. And this takes into account your asymptote. Right, and remember we defined that x is an element of real numbers. We may also write that x lies between negative 2 and 2, union to 6. Remember, the round brackets means we include the value. Sorry, the square brackets means we include the value. The round bracket means we exclude 2 because 2 is an asymptote. I've copied the example down again because we may solve this question using algebra. The reason why we can do this is because we have the absolute of x minus 2. Now we know that the absolute value is always positive by definition of the absolute value. So we can cross multiply across by the absolute of x minus 2. And this is a rare case where you can do it. So you can say that 4 is greater than or equal to the absolute of x minus 2. And we can rewrite it as the absolute of x minus 2 is less than or equal to 4. And we can only do this because we know that the absolute of x minus 2 is never negative. But we must bear in mind that we have the restriction that x cannot equal to 2. Because for two reasons. One, division, if you substitute x equals to 2 here, you will get a 0, and division by 0 is undefined. And that resulted, as you had a look at the graph, as it is an asymptote on the graph. So we're going to solve this inequality. So we may say that x minus 2 is less than or equal to 4, or x minus 2 is, the negative of x minus 2 is less than or equal to 4 by definition of an absolute value. So we have that x is less than or equal to 6, or minus x plus 2 is less than or equal to 4. We take 2 across, so we have negative x is less than or equal to 2. We divide left-hand side and right-hand side by negative 1, and that changes the direction of the inequality. So we got x is greater than or equal to negative 2. And the reason why I'm doing this in two parts is because of my restriction. And I can leave my answer in this format, taking note that x cannot equal to 2 is a restriction to the solution.